Welcome to this lecture on one-dimensional transient heat conduction. We will walk through why transient analysis is more complex than steady state, set up the governing equation and boundary conditions, explain step by step why we need separation of variables, derive the non-dimensionalized form to obtain homogeneous boundary conditions, complete the analytical solution, and finally introduce the one-term approximation and Heisler charts. This lecture follows Chapter 4 of Cengel's heat transfer textbook. Here is the roadmap for this lecture. Part 1. We justify why transient heat conduction is complex compared to steady state. Part 2. We start with governing differential equation for one-dimensional transient heat conduction and set up the governing partial differential equation and boundary conditions for a plane wall. Part 3. We explain why we need separation of variables, and why we must non-dimensionalize temperature to get homogeneous boundary conditions. Part 4. We carry out the full analytical derivation step by step. Part 5. We identify the practical limitations of the analytical approach. Part 6. We introduce Heisler charts as the standard engineering solution. Part 1. Why is transient heat conduction complex? Look at the animation on screen. In steady-state conduction, temperature depends only on position x, time does not appear at all. The governing equation is simply d squared t over dx squared equals 0, an ordinary differential equation you integrate twice and you are done. The solution is a simple straight line connecting the two boundary temperatures. It never changes. It is fixed forever. But now look at the transient case. Temperature depends on both position and time simultaneously. Watch how the temperature profile inside the wall evolves continuously as time increases. At time 0, the whole wall is hot. As time passes, heat escapes from the surfaces and the profile curves and flattens. Eventually it approaches the steady-state line. Every snapshot at a different time gives a different profile, t is a function of x and t. This introduces a partial differential equation in two independent variables, making the mathematics fundamentally harder. You cannot simply integrate once and find the solution. Part 2. Problem setup. Consider a large plane wall of total thickness 2L. We want to analyze the temperature distribution in the wall as it cools down or heats up over time. Now we should assign boundary conditions. This can be solved using one-dimensional transient heat diffusion equation. It gives us the rate at which temperature changes with time at any location in the wall, and now we should assign an initial condition and two boundary conditions as it is second-order differential equation. We have to be very careful and precise in setting up the problem, because the initial and boundary conditions are critical to the solution method. To assign initial condition, let us visualize that the whole wall is initially at a uniform temperature Ti at time t equals 0, or in other words before the cooling or heating process begins, temperature throughout the wall is uniform. Now let us focus on the boundary conditions. At time t equals 0, both surfaces are suddenly exposed to the environment at a temperature Ts. Therefore, the surface temperature at both sides of the wall instantly changes from Ti to Ts, so the boundary conditions are T at x equals 0 equals Ts, and T at x equals L equals Ts, and the wall is held there for all future time. Due to thermal symmetry about the midplane at x equals 0, we analyze only half the wall, from x equals 0 to x equals L. The governing partial differential equation is the heat diffusion equation, partial squared t over partial x squared equals 1 over alpha times partial t over partial t, or alpha equals k divided by rho Cp is the thermal diffusivity. Now, quickly try to understand the meaning of thermal diffusivity, that is alpha here. Thermal diffusivity alpha is a measure of how quickly heat diffuses through the material. Thermal conductivity K, which is in numerator, decides the diffusion of heat through the wall, whereas volumetric heat capacity rho Cp, which is in the denominator, decides how much energy is needed to change the temperature of the wall. Or in other words, how much energy is stored in the wall per degree of temperature change. This decides the transient behavior of the wall. Now we have the full problem set up, the governing PDE, the initial condition, and the boundary conditions. So let us move on to the solution. Now we have to follow separation of variables approach to solve this PDE. Why do we need separation of variables? The heat equation is a linear partial differential equation. Separation of variables is the classical technique for solving linear PDEs with constant coefficients. The key idea is to assume that the solution can be written as a product, t of x and t equals x of x times t of t, one function of position multiplied by one function of time. Substituting this into the PDE and rearranging separates the two variables onto opposite sides of the equation. Each side must then equal the same constant, splitting the single PDE into two separate ordinary differential equations that are each much easier to solve. Now let us understand why separation of variables fails if we directly apply it to the original problem with the given boundary conditions. Here is the critical problem. Our boundary conditions are t at x equals 0 equals ts, and t at x equals L equals ts. These are called non-homogeneous boundary conditions because the right-hand sides are not 0. Let us see why separation of variables fails directly. To save the video time, I have displayed screenshot of the full derivation on the screen and attached the same in description box for you to read at your own pace. If we assume t of x and t equals x of x times script t of t, and substitute into the boundary condition at x equals 0, x of 0 times script t of t equals ts. The left side is a product that depends on time, while the right side ts is a constant. This cannot hold for all values of time unless x of 0 equals 0 and ts equals 0. But ts is not 0, it is a prescribed temperature. Therefore direct separation of variables does not work. We must first transform the problem introducing non-dimensionalized temperature theta, which converts the non-homogeneous boundary conditions to homogeneous ones. Before introducing the excess temperature, let us think physically. Ask the question, if we allow the system to run forever, what temperature distribution remains in steady state? At steady state, the temperature no longer changes with time, so the time derivative is 0. The heat equation reduces to d squared TSS over dx squared equals 0. Integrating twice gives a straight line, TSS of x equals a times x plus b. Applying the boundary conditions, at x equals 0, TSS equals TS, so b equals TS. At x equals L, TSS equals TS, so A equals 0. Therefore TSS of x equals TS, a uniform temperature equal to the surface temperature. This makes physical sense. Eventually the wall reaches the surface temperature everywhere. Now we write the total temperature as the steady part plus a transient part, T of x and T equals TSS of x plus V of x and T. Here V represents the transient deviation from the final steady state. Now we introduce the excess temperature theta, defined as theta equals T minus Ts. Physically, theta tells us how far the local temperature is from the final surface temperature Ts. Since Ts is a constant, the time derivative of theta equals the time derivative of T, and the spatial derivative of theta equals the spatial derivative of T. The governing PDE in terms of theta becomes partial squared theta over partial x squared equals 1 over alpha times partial theta over partial t. Now look at the boundary conditions. At x equals 0, theta equals t at 0 minus ts equals ts minus ts equals 0. At x equals L, theta equals t at L minus ts equals ts minus ts equals 0. Both boundary conditions are now 0, these are homogeneous boundary conditions. The initial condition becomes theta at x in time 0 equals ti minus ts, which is a constant we can call theta I. Now separation of variables can be applied directly. Therefore, to make the solution as general as possible, we further non-dimensionalize. Non-dimensionalization is not magic, it is simply dividing each variable by a suitable reference quantity so that the result is a pure number with no units. We define three dimensionless groups, one for temperature, one for position, and one for time. Let us go through each one carefully. First, dimensionless excess temperature, capital theta. We take the excess temperature theta, which is T minus Ts, and divide it by the initial excess temperature theta I, which is Ti minus Ts. So capital theta equals theta over theta I equals T minus Ts, all divided by ti minus ts. Notice that at time 0, t equals ti, so theta equals 1. As time goes to infinity, t approaches ts, so theta approaches 0. Capital theta is therefore a dimensionless measure of how much temperature change remains. It starts at 1 and decays to 0. Second, dimensionless position x equals x over L. This simply maps the physical distance x, which runs from 0 to L, into the dimensionless range 0 to 1. Third, dimensionless time, known as the Fourier number, tau equals alpha t over L squared. Physically, the Fourier number represents the ratio of the rate of heat conducted to the rate of heat stored in the material. A large Fourier number means a lot of conduction has occurred relative to storage. The body is well into the transient process. Now let us substitute these three dimensionless groups into the governing PDE and see what happens to the equation. The original PDE is partial squared t over partial x squared equals 1 over alpha times partial t over partial t. We write t equals ts plus theta times theta I, where theta I equals ti minus ts is a constant. So partial t over partial x equals theta I times partial theta over partial x. And since x equals x over L, we have partial x equals L times partial x. Therefore partial t over partial x equals theta I over L times partial theta over partial x. Taking the second derivative, partial squared t over partial x squared equals theta I over L squared times partial squared theta over partial x squared. Similarly for the time derivative, partial t over partial t equals theta I times partial theta over partial t. Since tau equals alpha t over L squared, we have partial t equals L squared over alpha times partial tau. So partial t over partial t equals theta I times alpha over L squared times partial theta over partial tau. Substituting everything back into the PDE and cancelling theta I on both sides, the governing equation simplifies beautifully to partial squared theta over partial x squared equals partial theta over partial tau. Notice there is no alpha, no L, no ti, no ts. All physical parameters have been absorbed. This is the power of non-dimensionalisation. Now let us transform the boundary conditions and the initial condition using the same dimensionless variables. Recall the original boundary conditions were t at x equals 0 equals ts and t at x equals L equals ts, and the initial condition was t at x and t equals 0 equals ti. Substituting for the boundary condition at x equals 0, theta at x equals 0 equals t at x equals 0 minus ts, all divided by ti minus ts, which equals ts minus ts over ti minus ts, which equals 0 over something, which is 0. Similarly for the boundary condition at x equals 1, theta equals 0. Now for the initial condition, at t equals 0, t equals ti everywhere, so theta equals ti minus ts divided by ti minus ts, which equals 1. So the fully dimensionless problem is, PDE, partial squared theta over partial x squared equals partial theta over partial tau. Boundary condition 1, theta at x equals 0 equals 0, homogeneous. Boundary condition 2, theta at x equals 1 equals 0, homogeneous. Initial condition, theta at x and tau equals 0 equals 1. This is now a clean, beautiful problem that separation of variables can handle perfectly. All three dimensionless parameters, by tau, x, appear naturally in the solution. Part 4, the analytical solution. We now have the clean dimensionless problem with homogeneous boundary conditions. Step 1, we apply separation of variables. The key assumption is that the solution theta of x and tau can be written as a product of two functions, one depending only on position x, and one depending only on time tau. We write, theta of x and tau equals f of x times g of tau. Now substitute this product into the dimensionless PDE. The left side becomes f double prime times g, where f double prime means the second derivative of f with respect to x. The right side becomes f times g prime, where g prime means the derivative of g with respect to tau. So we have f double prime times g equals f times g prime. Now divide both sides by f times g. The left side becomes f double prime over f, which is a function of x only. The right side becomes g prime over g, which is a function of tau only. Here is the key argument: the left side depends only on x, and the right side depends only on tau. x and tau are independent variables. The only way two functions of completely different variables can be equal for every possible value of x and tau is if both sides equal the same constant. We call this constant negative lambda squared. We choose a negative constant deliberately because physically the temperature must decay towards steady state. A positive constant would give exponentially growing solutions, which is physically impossible here. Setting each side equal to negative lambda squared splits the single PDE into two ordinary differential equations, f double prime plus lambda squared f equals 0, this is the spatial OD, and g prime plus lambda squared g equals 0, this is the temporal ODE. Step 2. Solve the temporal ODE. The equation is g prime plus lambda squared g equals 0. This is a simple first-order linear ordinary differential equation. Let us solve it step by step. Rearrange, g prime equals negative lambda squared g. This says the rate of change of g is proportional to g itself, the hallmark of exponential behavior. Separate variables, dg over g equals negative lambda squared d tau. Integrate both sides, the integral of dg over g is natural log of g, and the integral of negative lambda squared d tau is negative lambda squared tau. So natural log of g equals negative lambda squared tau plus a constant of integration. Exponentiating both sides, g of tau equals c times e to the power of negative lambda squared tau. Here c is an arbitrary constant to be determined later. The negative exponent confirms that g decays exponentially towards 0 as time increases, which corresponds physically to the temperature approaching steady state. Step 3. Solve the spatial ODE. The equation is f double prime plus lambda squared f equals 0. This is a second-order linear ordinary differential equation with constant coefficients. To solve it, we try a solution of the form f equals e to the power mx, substituting m squared plus lambda squared equals 0, so m equals plus or minus I lambda, where I is the imaginary unit. The general solution of a second-order ODE with complex conjugate roots m equals plus or minus I lambda is if f of x equals c1 cosine lambda x plus c2 sine lambda x. Now we apply the first homogeneous boundary condition, f at x equals 0 equals 0. Substituting x equals 0, c1 cosine 0 plus c2 sine 0 equals 0. Cosine of 0 is 1, and sine of 0 is 0. So c1 times 1 equals 0, which means c1 equals 0. This eliminates the cosine term entirely, and the spatial solution simplifies to f of x equals c2 sine lambda x. The second boundary condition f at x equals 1 equals 0 will be applied in the next step to find the allowed values of lambda. Before we proceed to apply the second boundary condition, let us pause and understand a very important concept that we are about to use: eigenvalues and eigenfunctions. When we solve a boundary value problem like f double prime plus lambda squared f equals 0 with conditions f at 0 equals 0 and f at 1 equals 0, we are not solving for a specific function, we are asking, for which values of lambda does a non-trivial solution exist? These special values of lambda are called eigenvalues. Eigen is a German word meaning characteristic or own. These are the characteristic values that the problem itself picks out. The corresponding solutions fn of x are called eign-functions. Each eigenvalue lambda n gives its own eigenfunction fn of x equals sine lambda nx. Why do eigenvalues matter here? Because the full solution is built by superimposing all eigenfunctions together. The general solution is an infinite sum. Theta equals the sum over n from 1 to infinity of cn times fn of x times gn of tau. Each term fn of x times gn of tau is one eigensolution. It satisfies the PDE and both boundary conditions on its own. The coefficients cn are determined by the initial condition. Another key property of eigenfunctions is orthogonality. Two different eigenfunctions fm and fn are orthogonal. Their integral product over the domain is 0 when m is not equal to n. This orthogonality property is what lets us isolate each coefficient cn when we apply the initial condition. Think of it like Fourier series: each sine function is orthogonal to all others. Step 4. Apply the second boundary condition to find the eigenvalues. Recall the spatial solution is f of x equals c2 sine lambda x. Now apply the second boundary condition, f at x equals 1 equals 0. This gives c2 sine lambda equals 0. c2 cannot be 0 because that would give the trivial zero solution, no temperature variation at all, which is useless. So we must have sine of lambda equals 0. Sine equals 0 when its argument equals n pi, where n is any positive integer. Therefore lambda n equals n pi, for n equals 1, 2, 3, and so on. These are exactly the eigenvalues of this problem. Each eigenvalue gives one eigenfunction, fn of x equals sine n pi x. The corresponding temporal solution for the nth mode is gn of tau equals e to the power of negative n squared pi squared tau. So each complete eigensolution is sine n pi x times e to the power negative n squared pi squared tau. Now, for the more general case where the surface boundary condition is convective, meaning heat is transferred by convection with heat transfer coefficient h, the second boundary condition involves the Biot number. Applying it gives the transcendental eigenvalue equation, lambda n times tangent of lambda n equals the Biot number. This equation cannot be solved analytically, it must be solved numerically. It has infinitely many roots, lambda 1, lambda 2, lambda 3, and so on. Graphically, the roots are the intersections of the curve lambda tan lambda with the horizontal line at height bi. These eigenvalues are tabulated in Cengel's textbook, Table 4-2. Step 5. Apply the initial condition to find the Fourier coefficients. By superposition, the general solution is the infinite sum of all individual eigensolutions. At tau equals 0, the initial condition states theta equals 1 everywhere. Substituting tau equals 0, the sum over n of Cn sine lambda nx equals 1. This is a Fourier sine series expansion of the constant function 1. To isolate Cm for a specific mode m, we multiply both sides by sine lambda mx and integrate from x equals 0 to x equals 1. Here is where orthogonality does its work. The integral of sine lambda mx times sine lambda nx from 0 to 1 equals 0 whenever m is not equal to n, and equals 1/2 when m equals n. So on the left side, only the n equals m term survives. This gives Cn times the integral of sine squared lambda nx from 0 to 1 equals the integral of sine lambda nx from 0 to 1. Using the eigenvalue equation and standard trigonometric identities, the final result for the coefficient is Cn equals 4 sine lambda n, divided by 2 lambda n plus sine of 2 lambda n. With all coefficients known, the complete exact analytical solution is theta of x and tau equals the infinite sum of Cn sine lambda nx times e to the power of negative lambda n squared tau. This is the exact closed-form analytical solution for transient heat conduction in a plane wall. Let us apply this to a numerical example. Wall thickness 2L equals 0.2 meters, initial temperature 100 degrees Celsius, surface temperature 20 degrees. Thermal diffusivity 1.2 times 10 to the minus 6. Find the temperature at the center after 1000 seconds. Step 1. Fourier number tau evaluates to 0.12. Using the one-term approximation for the first term at the center, we calculate dimensionless temperature theta is approximately 0.306. Solving for actual temperature T gives 44.5 degrees Celsius. Part 5. Why is the analytical solution not the preferred method in practice? First, it is an infinite series, summing many terms is tedious. Second, the eigenvalue equation must be solved numerically per Biot number. Third, it depends on three parameters simultaneously, by, tau, and x. Fourth, cylindrical and spherical geometries introduce complex Bessel functions. Fifth, for practical engineering, the computational effort exceeds the accuracy of the input data. Part 6. Heisler Charts. M.P. Heisler recognized that the one-term approximation, valid for Fourier numbers greater than 0.2, gives less than 2% error. Because the solution depends only on bi and tau for the center temperature, the entire solution can be captured in just 2 charts per geometry. Grober added a third for total heat transfer. Chart 1 gives dimensionless center temperature. Chart 2 gives the position correction. Chart 3 gives total heat transfer. How to use Heisler charts. Step 1. Calculate the Biot number. Step 2. Calculate the Fourier number and verify it is greater than 0.2. Step 3. Read the dimensionless center temperature θ0 from chart 1. Step 4. If needed, read the position correction from chart 2 and multiply. Step 5. Recover the actual temperature. Step 6. Read total heat transfer from chart 3. Important validity conditions for Heisler charts. 1. Large plane wall, long cylinder, or sphere. 2. Fourier number must be greater than 0.2. 3. Constant thermal properties. 4. No internal heat generation. 5. Uniform initial temperature. If the Biot number is less than 0.1, use lumped system analysis instead. In next video we will cover how to use these charts and the underlying assumptions in more detail. To summarize, transient analysis is complex because temperature is a function of both position and time. Our boundary conditions are non-homogeneous, so we introduce x as temperature to make them homogeneous. After non-dimensionalisation, separation of variables applies cleanly to yield an exact analytical solution. Though exact, this is impractical for routine engineering work. Heisler charts present the one-term approximation graphically, valid for Fourier numbers greater than 0.2. Thank you for watching this detailed lecture on one-dimensional transient heat conduction analysis. For further study, refer to Chapter 4 of Cengel's Heat Transfer, 2nd edition.